Hello, everyone. Today we're going to dive into some fundamental concepts in probability, compound events, and the principle of inclusion-exclusion. By the end of this first part, you will be able to identify and define subsets of a standard deck of cards, and you'll be able to represent compound events using set notation, like unions and intersections. We'll start with compound events, which are events made up of two or more simpler events. To explore this, we'll use a familiar tool, a standard deck of playing cards. A deck of cards is perfect for this because it's a set of 52 unique items that can be grouped into many different subsets, like suits or values. This allows us to clearly demonstrate how unions and intersections of these subsets work. First, let's establish a clear notation for the cards. We'll use a two-character code. The first character represents the value, and the second represents the suit. For example, 7H stands for the 7 of hearts. K's is the king of spades. 3C is the 3 of clubs. And for the 10, we'll use the letter T, so TD is the 10 of diamonds. Using T instead of 10 ensures every card is identified by exactly two characters. Here is the entire deck of 52 cards laid out using this notation. Notice the 4 rows correspond to the 4 suits, and the 13 columns correspond to the values from ace down to 2. We have spades, hearts, diamonds, and clubs. The values are ace, king, queen, jack, 10, and then 9 down to 2. Now, let's define some of the key subsets we'll be working with. First, we have the suits. We'll use S for the set of all 13 spades, H for hearts, D for diamonds, and C for clubs. We can also group the cards by their value. K represents the set of all 4 kings, A for the 4 aces, Q for queens, J for jacks, T for tens, and so on for all the numbered cards. This is where unions come into play. We can create larger, more complex sets by combining these basic sets. For instance, the set of all red cards, which we'll call R, is the union of the set of hearts and the set of diamonds. This means a card is in set R if it is a heart or a diamond. Similarly, the set of all black cards, B, is the union of the set of spades and the set of clubs. We can also define sets based on other properties. Let's define E as the set of all even-valued cards. In our deck, this includes the sets of 2s, 4s, 6s, 8s, 10s, and queens. We consider the queen a face card with a value of 12, and the 10 as 10, both even. And the set of odd-valued cards, O, would be the union of 3s, 5s, 7s, 9s, jacks, and kings. We consider the jack to have a value of 11, and the king a value of 13, both odd. So to recap, we've established a notation for our deck of cards and defined various subsets based on suits, values, and other properties. We've seen how the concept of a union allows us to combine these simple sets into more complex ones, which is the foundation of studying compound events. Now that we have our sets defined, let's put them to use. In this section, our goals are to calculate probabilities of both simple and compound events using our deck of cards, and to apply set logic, like complements and intersections, to solve these probability problems. Let's ask a classic probability question. What is the probability of drawing a single card at random from a standard 52-card deck and having it meet certain criteria? Let's start with a straightforward example. First, what is the probability of not drawing a heart? We can solve this using the concept of a complement. The event not drawing a heart is the complement of the event drawing a heart. We write this as the probability of H bar equals 1 minus the probability of H. There are 13 hearts in a 52-card deck, so the probability of drawing a heart PH is 13 out of 52. The probability of drawing a heart is 13 over 52, which simplifies to 1/4. Therefore, the probability of not drawing a heart is 1 minus 1/4, which is 3/4. This makes sense as there are 3 other suits, each making up 1/4 of the deck. Let's try a slightly more complex problem involving an intersection. What is the probability of drawing a red card that is not a king? This question asks for the intersection of 2 sets, the set of red cards, R, and the set of non-kings, K bar. We can write this as the probability of R intersect K bar. This is equivalent to the probability of the set of red cards with the set of kings removed. We can think of this as the probability of R minus K. There are 26 red cards in the deck. Of these, 2 are kings, the king of hearts and the king of diamonds. So there are 26 minus 2, which is 24 red cards that are not kings. The number of red cards is 26. The number of red kings is 2. so the number of red cards that are not kings is 24. The probability is therefore 24 out of 52, which simplifies to 6 out of 13. Now, let's look at a simple intersection. What is the probability of drawing a red king? This is the probability of the intersection of the set of red cards R and the set of kings K. We need to find the cards that are in both sets. The kings are the king of spades, king of hearts, king of diamonds, and king of clubs. The red cards are all hearts and diamonds. The cards that are in both sets are the king of hearts and the king of diamonds. There are exactly 2 red kings, so the probability is 2 out of 52, which simplifies to 1 out of 26. Finally, let's look at a problem that will lead us into our next topic. What is the probability of not drawing an even card or a diamond? This is the complement of the event drawing an even card or a diamond. We can write this as the probability of the complement of E union D, which is 1 minus the probability of E union D. To solve this, we need to find the probability of the union of the set of even cards and the set of diamonds. How do we calculate the size of a union? If we just add the sizes of the 2 sets, we might be double counting. This is the problem that the principle of inclusion-exclusion solves. So, we've now practiced calculating probabilities for various events, using complements and intersections. We've also set the stage for our next key concept, which will help us handle unions correctly. Welcome back. In this section, we'll tackle the problem of calculating the size of a union of sets. Our learning objectives are to state and apply the principle of inclusion-exclusion for 2 and 3 sets, and to use this principle to solve counting and probability problems. Let's start with the principle of inclusion-exclusion. As we saw in the last example, when we want to find the probability of A or B, which is PA union B, we can't always just add P A and P B. Why not? Because we might count the elements in their intersection twice. Imagine 2 overlapping circles in a Venn diagram. If you count all the items in the first circle and then all the items in the second, you've counted the items in the overlapping region twice. To correct this, you need to subtract the size of that overlap once. This gives us the formula for 2 sets. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. This is the principle of inclusion-exclusion for 2 sets. Let's apply this to the problem we ended with, finding the probability of drawing an even card or a diamond. We need to find P of E union D. First, let's find the probability of each individual event. The set E of even cards contains 6 values, 2, 4, 6, 8, 10, and queen. Each value has 4 suits, so there are 6 times 4 or 24 even cards. The probability of drawing an even card, PE, is 24 over 52. The set D of diamonds contains 13 cards, so the probability of drawing a diamond P of D is 13 over 52. Now, we need the intersection, the cards that are both even and diamonds. These are the 2, 4, 6, 8, 10, and queen of diamonds. There are 6 such cards, so the probability of their intersection is 6 over 52. Now we can apply the formula. P of E union D equals P of E plus P of D minus P of E intersect D. Plugging in our values, we get 24 over 52 plus 13 over 52 minus 6 over 52, which equals 31 over 52. Remember, the original question was the probability of not drawing an even card or a diamond. So we take the complement, 1 minus 31 over 52, which gives us our final answer of 21 over 52. The principle naturally extends to more sets. What about for 3 sets, A, B, and C? If we add the 3 sets, we've double counted the 3 areas where 2 sets overlap, so we subtract those. But in doing so, we've subtracted the central region where all 3 overlap 3 times. Since we originally added it 3 times, it's now been completely removed. We need to add it back in once. This gives us the formula for 3 sets. We add the probabilities of the individual sets, subtract the probabilities of all the pairwise intersections, and finally, add back the probability of the intersection of all 3. This pattern of adding and subtracting is why it's called the principle of inclusion and exclusion. We have now seen how the principle of inclusion-exclusion provides a systematic way to calculate the size or probability of the union of sets by correcting for overlaps. We've applied it for 2 sets and seen the formula for 3. Let's work through another example, this time applying the principle of inclusion-exclusion for 3 sets. By the end of this scene, you will be able to apply this principle to a problem involving the divisibility of integers. Suppose we have the set of consecutive integers from 1 to 20. Our goal is to find the number of integers in this range that are divisible by 2, or by 3, or by 5. First, let's define our sets. Let W be the set of numbers divisible by 2. Let T be the set for numbers divisible by 3, and let F be the set for numbers divisible by 5. We want to find the size or cardinality of the union of W, T, and F. We'll use the three-set inclusion-exclusion formula. First step is to find the size of each individual set. For set W, the numbers divisible by 2 are the even numbers. From 1 to 20, there are 10 even numbers, so the cardinality of W is 10. For set T, the numbers divisible by 3 are 3, 6, 9, 12, 15, and 18. There are 6 such numbers. The cardinality of T is 6. For set F, the numbers divisible by 5 are 5, 10, 15, and 20. There are 4 of them. The cardinality of F is 4. Next, we need the sizes of the pairwise intersections. These are the numbers that are divisible by 2 different numbers. The intersection of W and T contains numbers divisible by both 2 and 3, which means they are divisible by 6. These are 6, 12, and 18. The size is 3. The intersection of T and F contains numbers divisible by both 3 and 5, meaning they are divisible by 15. The only one in our range is 15. The size is 1. The intersection of W and F contains numbers divisible by both 2 and 5, so they are divisible by 10. These are 10 and 20. The size is 2. Finally, we need the size of the intersection of all 3 sets. This set contains numbers divisible by 2, 3, and 5, which means they must be divisible by their least common multiple, 30. There are no numbers divisible by 30 in the range from 1 to 20, so the size of this intersection is 0. Now we have all the pieces. Let's plug them into the inclusion-exclusion formula. The formula is the sum of the individual sizes minus the sum of the pairwise intersection sizes plus the size of the three-way intersection. Plugging in our numbers, we get 10 plus 6 plus 4 minus 3 minus 1 minus 2 plus 0. This simplifies to 20 minus 6, which is 14. So there are 14 integers between 1 and 20 that are divisible by 2, 3, or 5. And there you have it. We've successfully used the principle of inclusion-exclusion for 3 sets to solve a counting problem involving divisibility, showing how this principle is a powerful tool for handling complex OR conditions. All right, let's shift gears to another crucial concept in probability: independence. In this section, our objectives are to first define conditional probability and then use that definition to formally define what it means for 2 events to be statistically independent. To properly define independence, we first need to understand the idea of conditional probability. Conditional probability is written as P of A, a vertical bar B. This is read as the probability of A given B. What this means is we are calculating the probability of event A happening under the new condition that event B has already occurred. The occurrence of B might change the likelihood of A. In essence, we are shrinking our sample space down to only the outcomes where B is true. The formula for conditional probability is the probability of the intersection of A and B divided by the probability of B. Think of it this way: the new universe of possibilities is just B. The successful outcomes within this new universe are those where A also happens, which is the intersection A and B. Now we can use this to define independence. So what does it mean for 2 events, A and B, to be independent? Intuitively, it means that the occurrence of one event does not affect the probability of the other. Knowing that B happened doesn't give you any new information about the chances of A happening. Formally, we say that A and B are independent if the probability of A given B is simply equal to the original probability of A. The condition didn't change anything. We can combine our 2 formulas to get a very useful test for independence. If P of A has B, P A, and we also know that P of A intersect B, B, then we can set these equal. P of A equals P of A intersect B divided by P of B. If we multiply both sides by P of B, we get the most common and practical test for independence. 2 events A and B are independent if and only if the probability of their intersection is equal to the product of their individual probabilities. This is the equation we will use over and over to check for independence. To summarize, we've defined conditional probability PAB as the probability of A happening once we know B has occurred. We then use this to define independence as the case where knowing B doesn't change A's probability, which leads to the key test. PV intersect B equals PA times PB. Let's apply our new test for independence to a few examples. In this scene, you will learn to determine if simple events, like those from coin flips and dice rolls, are independent. For our first example, let's consider two separate actions: flipping a coin and rolling a standard six-sided die. Let event T be the coin coming up tails, and let event F be the die roll coming up as a 4. Are these two events, T and F, independent? Let's use our test. We need to calculate three probabilities: P of T, PF, and PT intersect F. The probability of getting tails on a fair coin flip, P of T, is 1/2. The probability of rolling a 4 on a fair six-sided die, PF, is 1/6. Now, what's the probability of their intersection? That is, what's the probability of getting tails and rolling a 4? Since the two actions are physically separate, there are 2 times 6, or 12 possible outcomes, like heads 1, heads 2, and so on. Only one of these is tails 4, so the probability of T intersect F is 1 out of 12. Now we check the condition for independence. Does P of T intersect F equal P of T times P of F? We have 1/12 on the left side. On the right, we have 1/2 times 1/6, which is also 1/12. The equation holds. Therefore, the events are independent. This matches our intuition. The outcome of the coin flip has no bearing on the outcome of the die roll. Let's try a case that might be less obvious, involving just a single die roll. Given a single fair die roll, let event W be that the value shown is divisible by 2. Let event R be that the value shown is divisible by 3. Are W and R independent? The sample space is 1, 2, 3, 4, 5, 6. Let's define our events and find their probabilities. Event W being divisible by 2 corresponds to the outcomes 2, 4, 6. There are 3 such outcomes, so P of W is 3 out of 6, or 1/2. Event R being divisible by 3 corresponds to the outcomes 3, 6. There are 2 such outcomes, so PR is 2 out of 6, or 1/3. Next, we need their intersection, W intersect R. This is the set of outcomes divisible by both 2 and 3. The only number in our sample space divisible by both 2 and 3 is 6. So the intersection is just the set 6, and its probability is 1 out of 6. Now let's perform the test. Does P of W intersect R equal P of W times P of R? We have 1/6 on the left. On the right, we have 1/2 times 1/3, which is 1/6. The equation is true. So, for a single die roll, the event divisible by 2 and the event divisible by 3 are independent. This might not have been immediately obvious, which is why having the formal test is so important. We've now successfully applied the test for independence to 2 different scenarios, one intuitive and one less so, demonstrating its utility in formally verifying independence. In this scene, we'll explore independence using a visual model. Our learning objective is to be able to analyze the independence of events using this area-based representation. Let's look at this geoboard example. Imagine a 10 by 10 grid of points, representing a sample space with 100 equally likely outcomes. The probability of an event is the fraction of the total area it covers. We have 3 events represented by colored rectangles. Event B, the blue region, covers 20 squares, so its probability is 20 out of 100. Event G, the green region, covers 40 squares, so PG is 40 out of 100. And event R, the red region, covers 12 squares, so PR is 12 out of 100. The overlapping areas represent intersections. We'll use this information to test for independence between these events. First, let's check if events G and R are independent. We need to compare PG intersect R with P of G times PR. Looking at the diagram, the intersection of the green and red regions is this darker area here. It's 4 units tall and 2 units wide, so its area is 8. So the probability of G intersect R is 8 out of 100. Now let's calculate the product of their individual probabilities. P of G times PR is 40 over 100 times 12 over 100, which is 480 over 10,000, or 4.8 over 100. Since 8 over 100 is not equal to 4.8 over 100, events G and R are not independent. Next, let's consider events B and G. From the diagram, the blue and green regions are right next to each other, but they do not overlap. This means they are mutually exclusive events. The intersection of B and G is empty, so the probability of their intersection is 0. The product of their probabilities is 20 over 100 times 40 over 100, which is 8 over 100. Since 0 is not equal to 8 over 100, B and G are not independent. This is an important point. If two events have non-zero probabilities and are mutually exclusive, they cannot be independent. If one happens, the other is guaranteed not to happen, so its probability changes. Finally, let's check R and B. The intersection of the red and blue regions is the top right corner, which is a 2 by 2 square. Its area is 4. So the probability of R intersect B is 4 out of 100. The product of their probabilities is 12 over 100 times 20 over 100, which is 240 over 10,000, or 2.4 over 100. Again, 4 over 100 is not equal to 2.4 over 100, so R and B are also not independent. This geoboard example provides a clear, visual way to understand and test for independence. We've seen that we can determine independence by comparing the area of the intersection to the product of the areas of the individual events. To wrap up our discussion on independence, let's return to our deck of cards and work through a few more examples. The goal here is to solidify your ability to apply the test for independence to various events involving cards. First, let's consider the event H, drawing a heart, and the event Q, drawing a queen. Are these events independent? Let's find the probabilities we need for our test. There are 13 hearts in the deck, so the probability of drawing a heart is 13 out of 52, which simplifies to 1/4. There are 4 queens in the deck, so the probability of drawing a queen is 4 out of 52, or 1 out of 13. The intersection, H intersect Q, is the event of drawing a card that is both a heart and a queen. There's only one such card, the Queen of Hearts. So the probability of the intersection is 1 out of 52. Now for the test. Does 1 over 52 equal 1/4 times 1 over 13? Yes, it does. So the events of drawing a heart and drawing a queen are independent. Let's look at a more complex case involving 3 events. Consider the events S, drawing a spade, J, drawing a jack, and F, drawing a face card. A face card is a jack, queen, or king. Are these events independent? When we have more than 2 events, we usually check for pairwise independence. Let's check the pair J and F. Are drawing a jack and drawing a face card independent? The probability of drawing a jack is 4 out of 52. The probability of drawing a face card, jack, queen, or king, is 12 out of 52. What is their intersection? The event jack and face card is just jack, because all jacks are face cards. So the probability of the intersection is just the probability of drawing a jack, which is 4 out of 52. Let's check the test. Does 4 over 52 equal 4 over 52 times 12 over 52? Clearly not. So J and F are not independent. This makes sense. If I tell you a card is a jack, the probability that it's a face card goes from 3/13 up to 1, or 100%. Let's do one final example. Are the events R, drawing a red card, and F, drawing a face card, independent? The probability of drawing a red card is 26 out of 52, or 1/2. We already know the probability of drawing a face card is 12 out of 52, or 3 out of 13. Their intersection, R intersect F, is the event of drawing a red face card. There are 3 face cards, J, Q, K, and 2 red suits, hearts, diamonds, so there are 3 times 2, or 6 red face cards. The probability of drawing a red face card is 6 out of 52, which simplifies to 3 out of 26. Now we test. Does 3 over 26 equal 1/2 times 3 over 13? Yes, it does. So drawing a red card and drawing a face card are independent events. And that concludes our lecture on inclusion, exclusion, and independence. We've covered a lot of ground, from defining sets and compound events to applying formal principles and tests to solve probability problems. Thank you.